This will be the first of 2 lectures on dynamic programming. We'll start with a very simple, small example using a problem which, not really a problem, something which probably most of you will have seen maybe even multiple times. It's an example that's probably overused in intro courses as an example of recursion. But we're going to do something maybe slightly different than what you'll have seen. So the Fibonacci sequence is a sequence of integers defined as follows. F of 0 is 0, f of 1 is 1, and f of n is f of n minus 1 plus f of n minus 2. There's some other definitions in the literature which are very slightly different. All the major properties of the sequence remain the same for those, but the beginning can be slightly different. Anyway, this defines a sequence that looks something like this. And the first thing that's typically observed is this recurrence essentially tells us a naive recursive algorithm for computing the nth Fibonacci number, right? So I'm going to call my procedure fib1 because I'm going to give you more than one, right? And given n, it says if n is 0, return 0. If n is 1, return 1. And otherwise, recursively compute the n minus first Fibonacci number and then the n minus second Fibonacci number, add them together and return the result. Okay, so what's the running time of this algorithm? Well, the time to compute the value of the nth number is some constant amount of work to do everything in here, plus the time to compute the n minus first number, plus the time to compute the n minus second number. So if we let the time be t of n, it's the time for the call on n minus 1 plus the time for the call on n minus 2 plus big O of 1 for the other stuff. And what is that? That's just the Fibonacci recurrence, right? So this gives us a value that's theta of f of n. So what's f of n? Well, there's a closed form, and there's some nice approximations. We're not going to get into them, but you can look it up and see that this is big theta of g to the n, okay, where g is this number, which is the golden ratio, which is not really important to us. What's important to us here is that this is exponential in n, right? G is a positive constant, right? And n is our variable. So this is exponential in n. And why is that? Well, because of this, you can see intuitively this recursive tree of recursive calls. For the case of 5, goes like this. To compute 5, you call recursively to compute f of 4 and f of 3. And the computation of f of 4 involves this tree. But when you get to f of 3, even though you've already computed f of 3, you recompute it from scratch again. Okay, so as soon as you observe that, right, fib of 1 shows up lots of times, fib of 2 shows up a bunch of times, fib of 3 shows up here more than once already. Right? You say, why don't we just record the values we've already computed? Okay, so this suggests a better recursive algorithm that uses memoization. That's the recording of values we've already computed for use later, right? Okay, so we'll have an array F in which we record the values we've already computed. Okay, and so we have a procedure that does some setup, right? It sets f of 0 to 1, 0, f of 1 to 1, sets f of I for all other values I to some special value that we'll call empty, since all the values in our sequence are non-negative, any negative number would do to plug in there, right? And then we return the result of calling this recursive function, which looks like this. on input n, if f sub n is empty, we need to compute it, right? If it's not empty, we just return it, right? If it's empty, we compute it by making 2 recursive calls, right? And then, store the result for later use, and then return the value we stored. So what happens when you do that? Well, that call looks like this. We still, to compute fib of 5, we still call fib of 4, which calls fib of 3, which calls fib of 2, which calls fib of 1, right? And fib of 0. But later, since we've computed fib of 2 here, later, when we make the call fib of 2 here, which we still make that call, that recursive call, but we just do a lookup instead of recomputing, right? So we carve off this work doesn't get done again, right? And we compute fib of 3 here. And so later, when f of 5 needs the value of fib of 3, well, it still then makes a recursive call to find it, but then it finds it just by doing a lookup and not doing recursive computation. So all this work is also saved. And you can kind of see what's happening, right? Is we're just computing fib of 2, and then fib of 3 by 2 lookups, and then fib of 4, right? And then fib of 5. Okay, so what's the running time? Well, the running time is theta of n, because intuitively, roughly speaking, a second call, right? One call to fib2r of I might involve some recursion, but a second call never involves recursion. It just involves a lookup. Okay. Sometimes the conclusion in introductory books after observing this is recursion is dangerous and you should maybe not use it. And this is not really an appropriate conclusion because recursion is useful. Everything is dangerous, right? Iteration is dangerous too. You can have an unbounded iteration, or you can iterate over something that's bigger than you think. The thing that's dangerous is using techniques without understanding or without thinking through what they do. Okay, anyway, having seen this, now it suggests another algorithm, which is the dynamic programming algorithm for computing Fibonacci numbers. Okay, I'll call my code fib of 3. And so I just start with, instead of doing the recursion, I just start down here and I just work my way up, computing each number in terms of the previous numbers by 2 lookups, right? So set f of 0 to 0, f of 1 to 1. And then for I from 2 through n, I just say, to get f of I just look up f of I minus 1, f of I minus 2, add them together and store them, right? Very little work involved. Okay, so now the conclusion here is often, well, fib 1 is exponential time, and fib 2, and especially fib 3, are linear time, right? We went from some exponential to some linear. This is a huge improvement. Okay, but actually this is not a correct conclusion. This is a huge improvement. It's an exponential improvement in the amount of work, but it's actually not the case that it's correct to call these functions linear time and exponential time, respectively. Why? Because when we say algorithm is A is linear time, this is a short form for the following. The time taken by algorithm A is big O of n, where n is the size of the input. Okay, so this is critical here because we have a call to fib 3 of x takes time theta of x. I've changed my variable here on purpose, okay? Fib 3 of x takes time theta of x, but x is not the input size, it's the input value. What's the input size? Well, for a value x, we need about log base 2 of x bits to encode it. So in any reasonable encoding, the size of the encoding is about log of some log of the value, okay? So if our input is size n, what's the value of the number? What's the value of that number that's represented by n bits? It's something about 2 to the n. Okay, so now what we get is that on an input of size n, fib3 takes time theta of the value, that's about 2 to the n. Okay, so that's actually an exponential time algorithm, right? Even though it's a really simple algorithm, because the input is tiny compared to the size of that array that you have to build and the iteration you do. And what about the first algorithm, the bad recursive algorithm? Well, fib1 of x takes time theta of g to the x, where x is the value, right? So on input of size n, that function actually takes time theta of g to the value. The value for an input of size n is 2 to the n, right? So g to the 2 to the n, this is doubly exponential time, okay? This is atrociously bad algorithm for something that's easy to compute. There are problems that are actually so hard that you need algorithms with that complexity, but this isn't one of them. Anyway, so I don't actually know the complexity of computing the nth Fibonacci number. There's a lot of very interesting techniques, and there's some things that are easy to find on the web that are interesting, but some of them are wrong. So I don't know, but this is the point of the lesson, right? One was a simple example of going from a recurrence to a recursive algorithm to a dynamic programming algorithm, which is more efficient than the obvious one. And the second is this little example of taking care in your analysis of running time to make sure that you've accounted for what the input size actually is when you do it. Okay, so on to a little bit more interesting example of dynamic programming. And that's weighted interval scheduling. So we've done interval scheduling before. We had greedy algorithms for some related problems, right? So our input is a set of intervals, just like the interval scheduling problems before, the problem we started the greedy algorithm section with. But in addition, we have weight values for each interval, okay? And if we have a set of intervals, then the weight of that set will be the sum of the weights of the intervals in the set. And now our problem in the first version of interval scheduling was just find the largest size compatible subset of the intervals. But this version is going to be find a compatible subset of intervals that have maximum value, right? So this may not be the largest size set. This is the set with a maximum value. And this is a little bit more involved. So if we have all values are 1, of course, it's just the same as interval scheduling, right? And we know that the earliest finish time first greedy algorithm is optimal. But it fails if we have values that are different from 1. And here's a very simple example. So I have interval 1 is like this, and its value is 1. Interval 2 has value 2. Interval 3 has value 10. And interval 3 has value 1. And I line them up, I order them by earliest finish time. And so the earliest finish time algorithm will pick it will pick this one, the first finishing time, right? Then this one is ruled out, okay? And it will pick this one. So that gives you value of what the greedy algorithm gives you 2, but the optimal, of course, is to not take this one, but to take this one, right? And get 10. So the optimal is 10. Okay, so that one doesn't work, and in fact, no greedy algorithm is known that works for this problem. But something else works efficiently, and so let's try to construct that. Okay, so suppose that we order intervals by non-decreasing finish time. Okay, and think about a simple case analysis. Suppose that O is an optimal solution, and consider the question of whether this particular interval, the last interval, is in there or not. Sorry for that. I just have to fix something. Okay, so what's the choice? Well, if V6 is in the optimal solution, then we know what? Let me just mark it. Suppose we select V6, then we know V5 and V4 are not, right? Okay, so what do we have? We have that the optimal solution consists of V6 plus an optimal solution for what's left after you take V6 and V5 and V4, which are incompatible with it, out of the equation, right? On the other hand, if V6 is in, okay, or sorry, V6 is not in the optimal solution, then what? Well, then you just have to figure out what's an optimal solution for the set of intervals that's the same as the original but doesn't contain V6. Okay, so this kind of sets us up for a recurrence and a recursive algorithm, just like we saw with Fibonacci numbers. Okay, so we'll order the jobs by non-decreasing finish time. And then I'm going to define for each I, P of I, which is the maximum J less than I such that F of J is less than SI. What is that? It's just the last job that ends before I starts, if there is such a job, and 0 if there's no such job, right? So what does that mean? Well, here's computation. So P6 is what? Well, choosing 6 rules out 5 and 4, but doesn't rule out 3. So P of 6 is 3, right? P of 5, if we select 5, also 4 is ruled out because it overlaps with 5. So the last job in the ordering that finishes before 5 starts is 3. So P of 5 is also 3. For 4, the jobs before 4 all, sorry, this is wrong, right? What's if we pick, pick 4, yes. So sorry for the slip, 4, right? What are the jobs before 4? Well, 3, 2, and 1, they all conflict with 4, right? So if we pick 4, nothing before it is compatible, so P of 4 is 0, etc. Okay, now define a little more notation, which is similar to things we've used before. Let O be an optimal solution. And we'll write opt for the value of O, right? Okay. And we'll write O sub j for the optimal solution for the subproblem consisting of intervals I through j. So obviously O is the same as O sub n. And opt j will be the value of OJ, right? The value of the solution, of the optimal solution for the first j intervals. So obviously opt n is the same as opt. Okay, now we know a couple of things. Opt j has to be the maximum, right? Same choice as last time, 2 cases as last time. It's either the value of j, vj, plus the value of the optimum solution for the things that come before it, opt of P sub j, or it's the optimal value of a solution for the set of intervals up to but not including j. Okay, so this is the recurrence that's going to give us a recursive algorithm. And we can decide also whether a particular object, a particular interval is in set j. Why? By doing the comparison of those two values. Okay. Okay, so let's build now our naive recursive algorithm, just like we did for Fibonacci. Okay, the recurrence gives us this algorithm. We'll assume the jobs are ordered by finish time and that P of j has already been computed and write the recursion. Okay, so opt of j is, if j is 0, we return 0, we're done. Otherwise, we take the max, right, of vj plus opt of P sub j, or opt of j minus 1. The max of those and return it, right? Just turning the recurrence into code. So two claims, opt1 of j returns opt of j, right? This algorithm returns the actual optimum for the first j intervals. And it's the proof by induction on j using this this recurrence, right, to go from an inductive hypothesis case to the inductive step. Okay, you can see page 255 of the textbook for that proof. And the second one is opt1 of n takes exponential time. And we're not going to prove that, and it's not even proven in the textbook, but they do on a sentence or two that overlaps this page change, suggest a particular input, family of inputs, on which it takes time that's exponential, provably exponential. And you can kind of see, here's a tree of recursive calls for opt1 called on interval 6 of the same example, right? This is the same example. There's the tree of recursive calls. Looks a lot like the tree of recursive calls for fib of 5, doesn't it? And you see the obvious problem is the same, of course, right? We compute, right? We have opt of 1 called lots of times. We have opt of 2 called lots of times, right? Here we call we do a computation to get opt of 3. And here where we need opt of 3 again, we do the same computation. And here we do the same computation again, etc. Okay, so we can fix it in the same way, right? By adding memoization to our recursion. And there we get, we'll add this memoization array, call it M, and it'll have the property that M sub j is opt of j, if opt of j has already been computed and is empty otherwise. Okay, so what's our function look like? If j is 0, return 0. If mj is not empty, we just return mj, right? And otherwise, we compute m sub j, right? Using 2 recursive calls, okay? Right? Store the value, right? We would compute the value using 2 recursive calls, and we store the value, and then we return the value. Okay, so what happens is, of course, we compute opt of 3 here, and here to find opt of 5, we make 2 recursive calls, right? Right, but they're both lookups. Okay, so oh, this one is not. This one has to be computed, but this one, when we get here, of course, opt of 3 has already been computed, so we don't have to do this work. And when we get here again to opt of 3, again, this call has to, oh, that should be a 4. Never mind, okay, but we've computed it, so we don't do the work in the recursive call. Okay, so 2 claims. This function also correctly computes the optimum values. Essentially the same proof, practically. And on the other hand, it takes time, big O of n. Okay, so here's a hand wavy argument. Every time you call this function, the recursive function, it does one of two things. It does a lookup, or it computes a new value for m. Okay, so all you have to do is check the number of times it has to compute a new value for m, right? And once it's computed a value, it never has to compute that value again. And there's only n different values, right? So it kind of seems like you only make order n calls. That's a bit hand wavy, and the argument on page 257 of the textbook is also a bit hand wavy, but if you kind of think about both versions, you can probably write a real proof. Okay, now what about the real solution we're after, the proper dynamic programming solution? How does it go? Well, we do this. We take our set of intervals, order the jobs by non-decreasing finish time, compute the values p sub j as before, set m of 0 to 0, and then for I from 1 to n, what do? We just compute, sorry, that's a j. We compute m sub j by taking the max, right, of the two other values, same as before, opt of p sub j and opt of j minus 1, okay? Except now we know both of these things are already in the table, right? That's our inductive hypothesis, okay? So we just compute these two values, take the max, and store it in m sub j. Okay, to construct the actual optimal solution, once we've computed m, we do kind of almost the same thing, except we don't have to compute the values pj. Okay, if j is 0, output nothing. If v sub j plus m of pj is at least m of j minus 1, output j followed by the solution for p sub j, and otherwise output the solution for j minus 1. Okay, so we'll claim now that I haven't stated. I guess I should claim that it computes the right values, and also that it takes time n log n. Why does it take time n log n? Well, time n log n to order the jobs, and then this loop, and this is just a constant amount of work for each interval, right? For each job, so total of order n time for that. Okay, now let's do a little bit more involved problem, the segmented least squares problem. Okay, so this is a very common thing. We have a collection of data points, x1, y1, through x, n, y, n, and they're ordered so that x1 is less than x2, which is less than x3, etc. Right? So very common data situation. The x's are times or steps in something like that. Okay, so it's common that we want to understand the trend in y as x varies, right? And a very common way to do that is to compute the line through the data points with the least squared error, right? So if these are our points, a line like this that somehow kind of captures the trend, right? So we define a line L by an equation y equals x plus b, and then the error for that line relative to the data is the sum of the squares of the differences between the y values in the data and the corresponding y values on the line. And you can actually just closed form compute that error, right? Compute the line. You can compute the line with minimum error by these two equations. And we're not going to look through them. We really don't care about them. They're in lots and lots of different places you find basic data analysis treated. you can find this, but the point for us is that these two values that you need to get this line have a closed form, and they're actually, everything you see in these things is linear time, so they're efficient. Okay. Now, but what about things where you have changes in trends, right? So if we see this data, right, we can find the least squares error line. It looks like this, but you might go and say, this is not, kind of doesn't seem to be describing what's going on. What's going on looks a lot like what these two lines show, right? It was kind of going along like this, and then suddenly it changes and it's increasing like this instead of slowly increasing, it's increasing fast, right? Or maybe this one, right? The least squares error line looks like this. You might say, this is not really representing my data. Maybe with these three lines, tell me actually what's going on there, right? It's increasing very slowly or not at all, and then it increases fast for a while, and then it goes to increasing very slowly. Okay, so the problem is to solve this problem. We're given this set of points plus a penalty value C, and we'll see in a second what C is for. And our goal is to partition the set of points into k contiguous segments, right? So that we can make, right, 3 here, 2 here. So we have line segments that cover the full sequence of points, okay? And we want to minimize some penalty. What's the penalty? Well, each line segment, we should compute the least squares error. So for each segment, for each of the blocks in our partition, we have a contiguous sequence of points from our input set. And we want to find the least squares error line for that segment. And we take the sum of the errors over all our segments. Okay. And then we need to make sure that we don't just cop out and let every pair of every two subsequent points be a line, so we'll get 0 error, right? We need to say we shouldn't have too many lines, okay? So we have a penalty C times K, where K is the number of segments, right? To make sure that we don't, to make sure we don't use too many segments. Okay, so what happens if we have too many segments is this cost gets too high, but if we have too few segments, we may wind up with our least squares errors becoming too high. And so the goal is to balance these in some sense. Okay, so the challenge here is there are exponentially many possible partitions, and we want an efficient algorithm. So we don't want to explore them all explicitly. Okay, so a little bit notation similar to what we've used before. Let opt_i be the value of the optimum solution for P1 through Pi. And so opt0 was just 0. Okay, and let Eij be the minimum error for any line fitting the subsequence Pi through Pj. Okay, and let O be some optimal partition. Now think about this. If the last segment of O is Pi through Pn, and the last segment of O contains Pn, that's for sure, right? Just a question of how long it is. It contains Pi through Pn, then the value of O is what? It's this, opt_n, is the error for this last line. So here's the setting, right? I have I. Everything from I on is in the last segment, and then I have something else going on here. Okay, so what's the penalty for this? It's the error for this line plus a cost of C, because we pay a cost of C for each line segment, right? Plus whatever the value of the optimal solution for everything up to I is there. Okay, so this gives us the following recurrence, which is almost obvious, but not quite. So we want to compute opt of J, where J is somewhere in the middle here. Okay, What do we do? Well, if we knew where the segment ending at j should start, we would just have this, right? But we don't know. So what we have to do is we have to consider all possible values of I, all places that segment might start. That segment might go from here, or it might go from here, or it might go from here, right? Okay, so we take the minimum over all values of I from 1 to 1 less than j of the error for the best fit line from I to j plus c, the cost of having a segment, plus opt of I minus 1, right? The value, the penalty value for whatever comes in the solution before I, right? For the chunk before I. Okay, so now we're going to just jump directly, instead of doing our little exercise with bad recursion and memoization, we'll just jump directly to our dynamic programming solution for the segment least squares problem. So our input is the sequence of intervals and our penalty value. Okay, we set m of 0 to be 0. M, of course, is an array of size n plus 1. It goes up to m sub n, right? The value for opt n. Okay, now we compute all the least squared errors for all possible line segments, right? So for each pair, ij with I less than j, we compute the error E sub ij for the segment pij, right? That's the least squares error, right? The optimal least squares error, okay? So we compute those, and then for I from 1 to, sorry, from j from 1 to n, we compute m of j as what? Using the recurrence, of course, the min over choices of I less than j of the error for the line ij plus a charge of c for having the line ij plus whatever the value of the optimal solution for the subsequence up to I minus 1 is. Okay, and finally we return the value in m sub n. Okay, so two claims again. This algorithm returns the actual optimum value. How do you do that? The usual thing, proof by induction on j using our recurrence star, which is of course directly in the algorithm, right? And 2, the algorithm runs in polynomial time. Okay, to see that, well, there's n squared pairs, or order n squared pairs ij to compute optimum lines for, and computing up each optimum line takes time order n, so you get big O of n cubed, okay, to compute all the eij's. Actually, if you're smart about it, it can be done in time big O of n squared, but we won't get into that. And then we have n calculations of values mj, and each of those takes time big O of n. Why? Because we have to run over the up to n choices for I, right? So that gives us n squared. So total time big O of n cubed for what we have written, and total time big O of n squared if you know how to be a little bit smarter about computing these eij. Okay, finally, as before, our main algorithm constructed the values, but not the actual solution. And we can do the same sort of thing to construct a solution, right? If j is 0, output nothing. And otherwise, we find the I that minimizes the value in that recurrence, right? And then we output the segment that it gives us, okay? Plus the result of computing the segments for all the intervals up to I. Okay, so we'll finish up just a few little slides here with some non-technical stuff. So I'm not sure who the very first person to do give a dynamic programming algorithm was, but the person who really made it a field was named Richard Bellman in the 1950s. And the name, so why is it called dynamic programming? Well, the name actually has an interesting story, more interesting than what's on this slide. But in any case, so he had been working with some other people on methods to solve a bunch of problems that were of interest in the Department of Defense in the US. But the Secretary of Defense hated mathematical things, and it was very mathematical. So they had to come up with a name that sounded cool, but didn't imply mathematics. So the word dynamic was very hot at that time. In fact, it's probably no accident that there's this huge US defense contractor called General Dynamics, and General Dynamics was founded in 1952 because the word dynamic was very in fashion then for cool things. Okay, so this slide is just a bunch of examples of application areas and programming algorithm and important algorithms, important dynamic programming algorithms. I'm not going to go through them. There's a picture of a random, I guess, selection of books on dynamic programming. It just illustrates it's a huge, huge, huge field of work. And we'll finish with a little, a very cute misattribution of a quote. Those who cannot remember the past are condemned to repeat it by dynamic programming, not actually by dynamic programming. But anyway, it's kind of a cute remark. And that'll be the end for this lecture.